emission and absorption spectra. Okay, now first let's talk about what exactly atomic spectra in general is. Well, it's when atoms emit or absorb light of certain wavelengths. It serves as evidence of electrons in atoms being capable of only transitioning between discrete atomic energy levels. Now, this word discrete is specific quantized energy levels that electrons can occupy within an atom. Now, here's a new term. What exactly is quantized? What does it mean? Well, it essentially is carried in defined packets so that certain variables such as energy levels can only have specific magnitudes. Now, specific magnitudes is what you need to keep in mind. Now, I'm going to introduce an analogy here that might help you understand this a little bit better. When entering a country legally, you might be familiar with an immigration kiosk, which is utmost mandatory to pass through. And there will be a person asking for your identification, papers, and last but not least, your visa. And that visa contains information that decides whether or not you'll be able to pass through and enter the country or be simply sent back to where you came from. Now let's take the example of the US. When the immigration officer requests you to hand over your passport, they first do it mainly because they want to verify your identification, but most importantly, to check whether or not you got the visa that allows you to enter the country. Let's say you have a Singapore visa or an Indian visa, and what you actually need is a US visa. Then they will simply send you off back to where you came from. And that's with all countries. Now let's translate this real life scenario into science, specifically in regards to atomic spectra. This will help us better understand this statement specifically. Okay. Now I'm going to draw a board diagram or a rough sketch of a board diagram with a ground state, which is this line over here, the very first line. It's 13.6 electron volts. This is electron volts. Then let's say, I'm just giving a rough estimation. I'm not really sure of the values over here. I don't know it by memory, but let's say this is 4.2, this is 5.8, 13.6, 2.8, and 1.1 electron volts. And wait, just another line over here, and this is 0. This line over here is 0. Okay. So, in order for an electron to be excited to the next energy level, it needs energy. But how much energy? Okay, so in order to find the amount of energy required for an electron to be excited, you need to find the difference in energy levels. So it's 13.6 minus 5.8. Let me just quickly calculate that over here. Okay, so a supply of energy of 7.8 electron volts needs to be transferred to this electron over here, to this electron, in order to be excited to this energy level. And this 7.8 is known as discrete, a specific magnitude in order for an electron to be excited. It can be 9 or 8. The value needs to be on the nose. it can vary by 0.2, 0.1. It needs to be exact in order for an electron to be excited, and that's what discrete atomic energy levels are. Now, this is an issue that many students have, and I hope I was able to clear that up using the analogy of an immigration kiosk and having the right passport in order to enter the country. And I'll be continuing on with the next topic. Please respond to the poll that we're going to be sending out in the community, and just select any option what you think is best fit with your opinion of this entire material that I've created for you guys, so that we can improve later onwards in the upcoming videos that are going to be posted. Okay. Next is emission spectra. Now, this is a process by which a low pressure gas is heated, and the molecular impact of it is that, as I said, it excites electrons to high energy levels. Now, when I was talking about providing this electron 7.8 electron volts to move on to the next energy level, I was talking about this. This is the source that I was talking about that provides the energy to excite electrons to higher energy levels. And when an electron transitions back to a lower energy levels, it emits a photon. And you may not know what exactly a photon is at the moment. However, later onwards in this video, I'm going to be talking about it and hopefully clear up any doubts that you have. Okay. Now, each transition corresponds to a specific wavelength of light, as demonstrated over here by these blue lines, which correlates to observable spectrum. This is the most common way of representing the hydrogen emission spectrum, where there's a dark background, and these white lines represent the specific wavelength of light. Now, over here on the side, you can see that n is equal to 2, n is equal to 3, 4, and 5. This is essentially an energy level, but represented in number 4. So the second, third, fourth, and fifth energy level. Alright, so what exactly is the absorption spectra? Well, it's produced by passing white light through a cool, low-pressure gas. This is extremely important, because if you look at the previous slide, this is heating a low pressure gas, while here it's through a cool pressure gas. So the environment is completely different. Okay. The molecular impact of this is electrons absorb photons with exact energy to excite themselves. Now, what exactly does exact energy mean? Well, it's a more informal way of saying discrete. Alright. Now, each absorbed photon corresponds to a specific wavelength. Linked to observable dark light in a continuous spectrum of wavelength. Now, here's the difference between emission spectra and absorption spectra. Let's go through them. As said before, this is heating a low pressure gas, while this is passing white light through a cool low pressure gas. Electrons transition back to a lower energy level and emits a photon. Here, it absorbs the photon. Okay. Now, each absorbed photon corresponds to a specific wavelength linked to observable light in a continuous spectrum. So continuous spectrum is for absorption spectra, and observable spectrum is falls under emission spectra. Now let's take a look at the diagrams over here. In hydrogen emission spectra, there are white strips representing wavelengths falling on a dark background. However, in hydrogen absorption spectra, there are black strips representing wavelengths falling on a white background. And I hope you understand the difference between the two.